In problem 3, we're looking at error correction codes again. In particular, Alice wishes to send 5 characters to Bob, but there's a 0.1 probability for each character to be corrupted during the transmission due to channel noise. Therefore, Alice wants to transmit m additional characters to correct these potential errors, and Bob uses the Reed-Solomon approach that's listed in the lecture notes to correct the errors. And one point of clarification here is that all n plus m characters are subject to this 0.1 probability of being corrupted. In part 1, we want to know if m equals 2, what is the probability that Bob gets Alice's message successfully? So, Bob can tolerate, we know from Reed-Solomon codes in class, that Bob can tolerate up to m over 2, which in this case is 1, corrupted characters. So, let's let C be the number of corrupted characters. Then, we know that the probability of success is the probability that C is less than or equal to 1. That is, that there are 1 or fewer errors. So you can also write this as the probability that C is equal to 0, no errors, plus the probability that C is equal to 1, exactly 1 error. So for the probability of C equaling 0, what we have is that every single character must have come through successfully. For a character to come through successfully, there's a 0.9 probability. So we have 0.9 times 0.9 once for each character. So we end up with 0.9 to the n plus m, which is 0.9 to the 7, because every single character has to be correct. So this is just for the probability that C equals 0. For the probability that C equals 1, one way to think about it is that we should choose exactly one of the characters to be corrupted. So we'll have, out of 7 characters, we can choose 1 to be corrupted. And then the probability that 1 is corrupted, that a particular 1 is corrupted, will be 0.1 for that one to be corrupted, times 0.9 for the other 6 to not be corrupted. So this on its own here represents, for example, if we have A, B, C, D, E, F, G as our bits, this is the probability, for example, that exactly A is corrupted. Or it's the probability that exactly D is corrupted. But it could be that A is corrupted or D is corrupted, we haven't picked one, and that's why we have this 7 choose 1. So this probability here is the probability that C equals 1 is 7 choose 1 times 0.1 times 0.9 to the 6. So this whole probability here is 0.9 to the 7 plus 7 choose 1 times 0.1 times 0.9 to the 6. And this works out to be about 0.85. So part 2 is very similar to part 1 in that Bob can still only tolerate m over 2, which is still 1 error. So we're still looking at the probability of success is the probability that C equals 0 plus the probability that C equals 1. So the probability that C equals 0 is still going to be 0.9 raised to some power, but in this case it's actually raised to the power of 8 because there are now m plus n equals 8 bits being sent. And similarly, for the probability that C equals 1, it's exactly the same logic as in part 1, but now we have 8 choose 1 times 0.1 times 0.9 to the 7. So if we add these together, we end up getting probability 0.81 of success. So what we saw in part 1 is that the probability of success is about 0.85, whereas in the part 2, the probability of success is about 0.81. So, by the above results, adding more characters is not always helpful, because the probability of success went down despite adding another character. So, after doing the calculations in part 1 and 2 and reaching the conclusion in part 3 that it doesn't help always to add more characters, Ellis starts to get really frustrated and wants to figure out some number of characters to add so that the probability of success is at least 0.9. So, we've tried m equals 2, m equals 3. Next thing to try is m equals 4. We could try to find some fancy way to solve this problem, but it seems like we're already pretty close to 0.9, so we'll just try m equals 4 and see if that works. So this means that we can tolerate m over 2 equals 2 corrupted characters. So now the probability of success is the probability that C is 0 plus the probability that C is 1 plus the probability that C is 2. And recall from the first part that C is the number of corrupted characters. So the probability that C equals 0 is again going to be 0.9 to the n plus m, which is 0.9 to the 9th in this case. The probability that C equals 1 is again going to be now 9 choose 1 times 0.1 times 0.9 to the 8. And now the probability that C equals 2, by very similar logic to the C equals 1 case, we're going to have 9 choose 2, because now there are 2 different bits we can choose to be corrupted. Then 0.1 squared probability, because we need the probability for each of these 2 bits to be corrupted, times 0.9 to the 7 for the other bits to not be corrupted. So when you add these all together, so you have 0.9 to the 9, so the probability of success is equal to 0.9 to the 9 plus 9 choose 1 times 0.1 plus times 0.9 to the 8 plus 9 choose 2 times 0.1 squared times 0.9 to the 7. And if you calculate this out, this ends up being about 0.95, which is greater than 0.9, so we have achieved our target. We've actually overshot our target, which is great. So m equals 4 is the right answer. Finally, we want to look at the more general case where n and m are any numbers greater than or even equal to 0. And there's some probability ranging between 0 and 1, which is the probability for each character to be corrupted. We want to figure out whether or not it is always true that adding 2 more characters is at least as good as transmitting the original number of additional characters. So is it always better or at least not worse, to add 2 more characters? So this turns out to be false, and we can actually find a really easy counterexample, really simple counterexample. So we'll say n is 1, we're trying to transmit only 1 bit of information. M equals 0, so originally the additional characters, we don't send any additional characters. And p is 0.9, so in this case, the probability of corrupting the characters is actually really high. So if we look at the probability of success using m, what we have is 0.1, because there's a 0.9 chance that that 1 character that's sent is corrupted, and there's a 0.1 chance that it's not corrupted. And now we want to look at the probability of success with m plus 2. So this is going to be the probability that we have 0 corrupted characters plus the probability that we have 1 corrupted character. And by the same logic as in earlier parts of the problem, this will be 0.1 to 3, and this will be 3 choose 1 times 0.9 times 0.1 squared. And if we add these together, we end up with actually 0.028, which is less than 0.1, which was the probability of success using M. So, in this case, we found that actually transmitting 2 characters of redundancy was worse than not transmitting any additional characters in this particular example. So it's not always true that adding extra characters is better.